Welcome to I Can Science That. This channel is devoted to honest investigation of everyday science. And with that in mind, I'd like to introduce you to Peter Leane, who has a small YouTube channel, and he is an experimentalist and an inventor who is doing just that, investigating everyday science and making some pretty advanced apparatus for trying to explore ideas of science. Right now, Mr. Leane here is looking at the Foucault pendulum, and he has been trying to make essentially a scale model, I guess, of the Foucault pendulum to explore how that works. I will, of course, include the link to this video down in the doobly-doo, so you can check it out down there if you want to see exactly how it works. Let me jump ahead and show a piece of this video so we can highlight the problem that he has run into. And here I've queued it up to a particular video where he's looking at it. Let's watch that briefly, and then we'll talk about it.
The pendulum moves off the center dot. It moves away by at least 10 millimeters, sometimes 15, maybe 20 millimeters. However, this pendulum does not. Why, when the Earth goes around with this pendulum, why doesn't it move? This is the same simulation. This is the Earth spinning. Here's the roof. Same pendulum. However, I get a movement in the pendulum. There's no need to swing it. Quite obviously, you would see a deviation off the centre point. So, that is my problem.
So the one on the right, he's got it on a turntable so that he can rotate it, hoping to simulate what the rotation of the Earth would do to a pendulum by putting a pendulum on a turntable, in the idea that that's analogous to the Earth's rotation. And immediately he sees that any tiny misalignment of the pendulum hanging on the right, on the turntable on the right, is very visible as he rotates the turntable. But he didn't have to be precise at all with the pendulum hanging from the ceiling, the one on the left, because he's not rotating that one. The question becomes, though, if the Earth is rotating it, why doesn't it suffer that same alignment issue that the turntable does? So let's investigate that a little bit. Okay, I've made myself a little simulation here in Unity that I like to use. I've got my Earth, my globe, and here the red arrow. I have programmed the red arrow to point specifically in the direction of gravity. With the latitude and longitude, I can adjust where I want the arrow to be, and I've got it at the North Pole. And at the North Pole, everybody gets the gravity vector right. It points straight down. So the question I want to ask everyone to stop and think about for a moment. If I move the gravity vector to another place on Earth, let's say I move it to about London. You can see right there in the center, there's England right there. Let's move it to England. What will the gravity vector look like at England? Let me pause for just a moment to acknowledge that there are some viewers who are going to be deeply disturbed by this presentation of what I think the world looks like and how gravity works on it. For those people, I would invite you to please recognize that what we're doing here is called a hypothesis. We can hypothesize that the Earth is this shape and that gravity works the way I'm proposing that perhaps it does. We would not jump to any conclusions about whether that hypothesis is correct or not until we have compared the results of these predictions that the hypothesis makes against real-world observations. So we've got some predictions that we're going to make today on this simulation based on that hypothesis, and we're going to compare them with the observations of Peter Leane and try to evaluate whether or not these predictions contradict those observations. Okay? So run with me here. And if we take the hypothesis that gravity is mass attracting mass, that what then should be the direction of gravity if I move my rig to England? Because England's right in the center screen there, let me move over a bit so we can see England over there. Maybe we'll get a better sense of which way gravity should point there. And then let's just drag this thing on down to right there, somewhere around there. Looks like about England. So hopefully everybody was with me that's the way that gravity works. Gravity points towards the center in this hypothesis. Gravity points towards the center of the sphere. And therefore, as I move to any point on the surface, the gravity vector is different from any other point on the surface. It should always point into the center, and that does give us always perpendicular to the surface everywhere on a sphere. I think that Peter Leane is in Australia, so let's go to Australia. I've got the latitude and longitude of Australia up here. Let's see, that's 33.87. I'm going to Sydney. I don't know where in Australia. It's big. It's a big country. And 151.21 east. So here it is over here. So that's about Sydney, Australia. And I think we can agree under this hypothesis that's the way the gravity vector should point. And let's look at it here in this simulation, this version of the same simulation, where I can just look at it like that, and then we can see if we look straight down the gravity vector, it is perpendicular to the surface there, pushing straight at the surface right at that location. These plumb bobs that Peter Leane is showing us are hanging straight down in what direction? They are hanging from the ceiling or from the top of the turntable straight down in the direction of parallel to the gravity vector, the local gravity vector. Whatever gravity is at this point, that's the direction these pendulums hang. And again, for my skeptical fans who don't like the idea of gravity as I've presented it, that's fine, as long as we understand that my terminology here, when I refer to the gravity vector, it's whatever causes plumb bobs to hang down. If it's not mass attracting mass and it is something else, whatever that may be, plumb bobs hang down. Let's call the direction that they hang gravity, okay? And I am hypothesizing that gravity should be pointing towards the center of a globe Earth. What happens to the local gravity vector when I rotate the whole ball 30 degrees to the east? Let's do it and find out. Let's take the Earth here, and I'm going to rotate it 30 degrees to the east, 20, 25. That's about 30. I type it in. There you go. It's exactly 30 degrees to the east. What happened to the gravity vector? Is the gravity vector off center from the surface now because of that? And the answer is no, because the gravity vector rotated with it. Everything rotated exactly in the same way. And hopefully we can see that. In fact, let's just, boom, kick off the Earth spinning. Watch what would happen if the Earth spins. What happens to the gravity vector? And we can watch it over here as well. Where is it? There it is. Here comes Australia. That gravity vector remains aligned with the surface while the surface is rotating. If the surface rotates, the gravity vector remains perpendicular to the surface at that point. And these plumb bobs are hanging in that direction. So that's why we do not expect to see any deviation of the plumb bob relative to the surface as we rotate. But how about this one? This one, why is it different? When we rotate this platform, we see that the plumb bob deviates away from its original position. Why does rotating this one cause the plumb bob to get off center when rotating this one we just saw did not? I have made a little simulation of that one as well. These two squares represent the turntable, and hanging from the top one, I again have a gravity vector. Here we go. That is once again programmed to point in the gravity direction, which is straight down. So regardless of what the turntable does, the plumb bob hangs from the mounting point, and the mounting point is indicated right here. From the mounting point, it hangs straight down, no matter what angle the turntable is at. So let's see how that reacts to turning the turntable. Let's turn the turntable. I don't know, it's like 90 degrees per second or something. There we go. We're spinning the turntable, and we can see that plumb bob hangs in a perfect location. It does not deviate around at all. It holds perfectly still. But in Peter Leane's example, that didn't happen. Let's see if we can explain that. What happens if we misalign it a little bit? What if the turntable is not perfectly balanced with the direction of the local gravity? Let's take the turntable mounting point down here, which is right here, and this is where the motor for the turntable is mounted. And let's just rotate it by 10 degrees. Okay, and now when I rotated it by 10 degrees, we can see it's not aligned anymore with the local gravity, and that's causing our plumb bob to hang off center. That's no problem. We can pull the plumb bob back on center. That's the way Peter Leane's video showed it, was that the plumb bob was perfectly centered. Let's get that back on center. We'll just move the mounting point so it's perfectly on center. There we go. And now let's just kick this thing off to a spin. Let's, here we go. 90 degrees per second. We'll spin it. And what do we see? Let's look at it in this view maybe. And now the plumb bob hangs, and it traces out a little circle on the turntable below it, coming back through the center point and then swinging out away from the center point. So back up through the center point, back away from the center point. Why is it doing that? If we look up here, we can maybe see it from the mounting point. If we look at the top, it's stuck to this point on the top of the rig. And so that point in the top of the rig is tracing out a little circle in the air above you because it's not aligned perfectly. Hopefully we can see that the top of the turntable where we've mounted our plumb bob is doing that. So Peter, hopefully this helps to explain why if you have a slight amount of misalignment in your turntable situation, you're going to get these little circles in the way the plumb bob hangs, because the top of the plumb bob is going around in little circles. And I think that would make an excellent follow-up video, is if you just, instead of focusing on where the plumb bob pointer is hanging, move the camera up and just look at the Plumb Bob's mount point and watch how the Plumb Bob's mount point is actually going around in a circle relative to the floor of the room. I guarantee that's what you're going to see, is because the Plumb Bob is hanging straight down. So the only way to make the end point move in a circle is if the top point is also moving in a circle. And so just take your camera mount where you've focused a little bit too much on the point of the Plumb Bob, and just look up and notice that the top of the Plumb Bob, from a fixed camera point of view, is actually going in a little circle. Whereas if the rig was not rotating, right? The rig was not rotating. Turn off the rotation. Now it's only rotating with the earth, right? If we don't have the turntable turning and we view it for 24 hours, we'll see that it holds perfectly steady because it is now bolted to the earth. It's connected directly to the surface. Any rotation that is happening to the ceiling and the floor together in the same amount. Or if you turn the turntable on, now there's a motion of the ceiling that does not match the motion of the floor. Finally, I think I should probably pause to point out that the turntable rig that you have set up here is not actually analogous to the rotation of the earth, because the direction that you are rotating is at least attempting to be perfectly parallel to the direction of the local gravity. But that's not how things happen on the earth. If I go back to the simulation here, we will notice that the earth's rotation goes that way, and that causes the gravity vector to go around at an angle. The only places on the earth where that axis of rotation and gravity vector align are at the geographical poles, at the geographical north and south pole. Only there would your scale model of a Foucault pendulum be the same thing that we are trying to model with this rotating earth. The problem is, really, you can't make the gravity vector change. We're stuck with the gravity vector that we've got. Okay, so in summary, the scale model of the Foucault pendulum needs to be aligned just right, or else it's going to make little circles on the ground, and that's to be expected. And then also the analogy that you're making here of the reduced scale model isn't really quite what the Foucault pendulum shows, except at the North and South Pole. But maybe there's something to still be learned from that simulation anyway. A real Foucault pendulum does what we call precession, because the gravity vector that the pendulum is hanging by gets misaligned with the original swing direction. Sometimes we hear that a Foucault pendulum swings in a plane and then the earth turns underneath you. Well, that's only true at the poles. Everywhere else, the pendulum is swinging like so, and then the earth turns, the gravity vector turns it, sideways. So like swinging a pendulum, and then the earth does this while you're swinging the pendulum. It can't stay in a plane. So the force of gravity and the swing direction get out of alignment, and that creates a three-dimensional rotational effect that we call precession. And that causes the pendulum to swing around. And that's why you also have the sign of the latitude in the equation. Right, we get different rotation rates at different latitudes, because it isn't swinging in a plane while the Earth is turning underneath it. It's actually precessing, and I haven't come up with any brilliant way to make a scale model of that. Of course, we can do scale models of precession and show precession with a gyroscope and things like that. But trying to make a very clear one-to-one analogy like you're doing, I don't have any easy answers for you. But hopefully this helps to understand why you're getting the little circles in your Plumb Bobs. That's it. So I'll see you guys out there.